Okay, the second type of full wave rectifier is called bridge. Bridge rectifier is using a normal transformer, and it has 4 diodes: D1, D2, D3 and D4. Okay, this is the slide show the operation of the bridge rectifier. So the first figures or the first picture show the condition where the input is at the positive half cycle. This is at positive half cycle. So here this is positive at the primary, positive. So this is a positive, this is negative. Okay, so since this is positive, so D1 is on because the positive at the anode, D3 is off because the positive at the cathode. So for the D2 is on because negative at the cathode, this is on, and D4 is off because negative at the anode. Okay, so in this condition, there will be a current flow across the RL, and the current flow will be along this line and this direction. Along this direction. So it will passes D2 and D1. Okay, so there will be an output voltage. When the input is at the negative half cycle, this is negative half cycle, so the diodes that will be turned on will be D3 and D4, because at here D3, the cathode of the D3 is connected to negative, so this forward bias, and the anode of the D4 is connected to the positive. So D2 and D1 will be in off condition. So now the current direction will be along this line. So that's why we can see the output voltage at the negative half cycle. Okay, so the previous slide we show you the waveform of the output. So basically the waveform of the output has the similar shape with the center tap because both are full wave rectifier. And then in this slide show you how much the peak voltage at the output. Okay, the peak voltage depend on the model that you use to for your analysis. If you replace the diode with the ideal model, so ideal model in fault bias, the diode is replaced by the short circuit. So short circuit, the voltage drop is 0, so the output will be equal to the secondary. So the output will be equal to V peak secondary. But if you consider a practical diode, so you will have the reduction of 1.4 volt. So reduction of 1.4 volt. This is because for each current pass, there are 2 diodes. Okay, so 2 times 0.7. Okay, so and then next we consider a peak inverse voltage. Peak inverse voltage, remember the peak inverse voltage actually the amount of the reverse voltage applied to the reverse bias diode. So when you consider a circuit, you need to find or you need to identify which diode is in the reverse bias, and then you need to calculate or determine the voltage across it. Okay, for example, let's say we consider the practical diode model here at the positive. This is at the positive input cycle. Okay, positive input cycle, this diode will be in forward bias as well as this diode. Okay, if we consider the number 1 diode, let's say put this number 1, the PIV is voltage positive at positive minus voltage at the negative. Okay, voltage at positive here, okay, equal to the V out, equal to the peak V out. So this is a V peak out. And then voltage at this negative here is equal to this point. This point is actually a negative 0.7 volt. Okay, VP out, during the previous slide analysis, VP out is V peak secondary minus 1.4, and then we have minus minus, this is plus 0.7. So lastly, we get V peak secondary minus 0.7. This is PIV for the practical diode model. Okay, for the practical diode model. For the PIV, in case of the ideal diode model, so if you consider this one, this PIV, consider this D4 here, the PIV is equal to V plus minus dengan minus V at the negative part. So V plus here is equal to V out. So V out without a diode voltage drop, it becomes V peak secondary. Okay, and then here, this is no voltage drop, so it's equal to 0, grounded. So equal to V peak secondary. Okay, but anyway, for PIV, let's focus only on the practical diode model. Okay, this table summarizes the equation, the related equation for the both forward full wave rectifier. So in terms of the output waveform pattern, this is the same because both are full wave rectifier. Okay, and then for the P out, you can see here for the center type, you need to divide by 2 because this is center type. And for the bridge, there will be a 2 times voltage drop because 2 diode for every current path or every current flow. Okay, and then in terms of the VL average also known as VDC, DC voltage. For DC voltage, the general equation is same, V peak out over pi. So you need to determine the VP out first. Okay, for the VRMS, same with the VDC. The general equation is similar, both for center tap and bridge, V peak out over square root 2. And then for the as well as PIV also the same.